All right, so we've been talking about implication, and I want to review a little bit about what we talked about in class. Implication is a statement of the form if-then, or P implies Q. Our notation is this double-stemmed arrow. We call P the hypothesis and Q the conclusion of this implication. And there's also a couple other ways to talk about this implication. We could say P is sufficient for Q, or Q is necessary for P. Let's remind ourselves what the truth table is for this particular function. So if we have P is true, true, false, false, and Q is true, false, true, false. So we've got all possible combinations of inputs, trues, and falses for our connective. Then P implies Q is true in the following situations: when both P and Q are true, when they're both false, when P is false and Q is true, and when P is true and Q is false, we get that this statement is false. Okay, we've seen another logical operator, logical connective that has 3 trues and a false in its truth table. So we might wonder if this is logically equivalent to some kind of or statement or disjunction, which is the other type of logical connective that has 3 trues and a false in its truth table. So keep that question in mind. We also might want to know, how do we negate an implication? And I've got this little conjecture here. I think that the statement not P implies Q is logically equivalent to an and statement, so P and not Q. And my strategy for showing that this is true is going to be to use a truth table. So let's sketch out a truth table here. We've got P and Q. We're going to get the intermediate P implies Q written out, and then we'll take the negation of that. And we want to compare this to P and not Q, so maybe I'll give myself a not Q column to gaze upon, and then I'll work out P and not Q. So let's take a crack at this truth table. I've got true, true, false, false for my P's, true, false for my Q's. Again, this ensures that I've got all possible combinations of these trues and falses for my P's and Q's. Glancing at the truth table a little bit above, I see that P implies Q has the column true, false, true, true, given these inputs, which means that the negation of this is going to be false, true, false, false. And I notice that I have 3 falses and a true, which remind me of the truth table for a conjunction or an and statement. So at least I know I have the right number of falses and trues. I just need to see if they align with the last column in this truth table that I'm building. Anyway, let's take a look at not Q. So not Q is going to be false, true, true. And then P and not Q, the only time that that is true is when P is true and not Q is true. So I get a true there. And otherwise, it's going to be false. So in these 2 situations, it's false because not Q is false. And in the final situation, it's false because P is false. And as I look at the truth table here, I see this column match up. So I can answer this question. I can say, yes, they're logically equivalent because they have the same last column. All right, now this is worth recording, right? It's good to know, how do you negate any of our logical connectives? So we've got the law of implication down here. Part B is what we just did. It says to negate an implication, you can turn it into an and statement that looks like this. And we're going to prove part A using part B and some of the other things that we've got. So proof of part B is the truth table above. And proof of part A we're going to string together a few logical equivalences. So the first thing that I know is that if I take P implies Q, that's logically equivalent to negating that twice. That's the law of the double negative. Double negative. right? I can do a not, and it's the same as not doing anything. I always want to tell a not joke, like a knock joke, but then I realized that no one's going to laugh at that, and so I don't. So I don't even know why I'm saying that right now, except to give you a chance to catch up if you're trying to take notes along with this video. Anyway, we apply the old not, which leaves everything unchanged. And now let's take a look at the inner not P implies Q. So we've still got this outer thing, but I'm going to transform the inner piece using part B. So part B tells me that this looks like P and not Q. So that's part B of the law of implication. Law of implication. All right, and now I'm negating an and statement, which means I can use De Morgan's laws. So the negation of an and statement becomes not P or not Q, right? I negate both of the component statements and I turn the conjunction, the and, into a disjunction, an or. So that's De Morgan's laws. Part A or part B, I don't care if you remember or I remember which one. And then we can use the law of the double negative again. So the not P stands alone, and this not Q becomes a Q. And we're done. We've gotten to the statement that we were hoping to get to. So that's the end of this little proof. And if you're thinking, gosh, this looks like a high school geometry proof, and Professor Gibbons promised us we weren't going to have to write high school geometry proofs, I guess I lied to you a little bit. For these short logical proofs, it really is going to be pretty much like what you did in geometry. You've got a few facts, and you line by line tell me which facts you're using as you transform one statement into another. But when we get back to proving mathematical statements, like statements about matrices and stuff, we will do some more interesting proofs than this. All right, one of our takeaways from the law of implication, and in particular part B of the law of implication, is that the negation of P implies Q is not as simple as just kind of like distribute the not. It's not the same as not P implies not Q. And in fact, we could see that with a truth table, and we're going to do that fairly soon. So once we have an implication, we could wonder what kinds of statements do we get if we switch around the hypothesis and the conclusion, or if we negate the hypothesis and conclusion, or if we negate the hypothesis and conclusion and switch them around. So let's work through the truth tables of those related statements and give them names. So this is our original implication, P implies Q. If we switch the conclusion and the premise, we get something called the converse. If we negate the premise and negate the conclusion, but leave them in place, we get something called the inverse. And if we negate the premise, negate the conclusion, and then swap their roles, we get something called the contrapositive. So let's see what happens as we work through the truth tables here. So we know that the truth table for P implies Q is going to be true, false, true, true. If I switch the Q and the P, well, I know an implication is false if both of its component statements are true or both of its component statements are false. It's also true if its premise is false and its conclusion is true, which means that when Q is false, then my statement is true, weirdly enough. And when Q is false, but P is true, or sorry, when Q is true, but P is false, we get a false here. So you see that the implication and its converse are not logically equivalent to one another. Okay, now we're gonna do this hard part. We're gonna do not P implies not Q, which means whenever, we know that the implication is true whenever the premise is false. So that tells me that when P is true, not P is false, which makes my implication true. My implication is also true when my premise is false, but my conclusion is true. So that would be the last row here. sorry, when they're both true. That's what I meant to say, right? When they're both true, my implication is true. And the only time it should be false is when the premise is true and the conclusion is false. So that means I'm looking for not P to be true, not Q to be false, which means I want P to be false and Q to be true. And I see here my first logical equivalence, the converse and the inverse are logically equivalent to one another. So those are the same, logically speaking. Let's take a look at the contrapositive. So the contrapositive, it's another implication. My implication is true whenever my premise is false, which means not Q should be false, which means Q should be true. So I can put a couple trues in here, wherever Q is true. It's also true when my premise is true and my conclusion is true. And that happens when P and Q are both false in this case. And so the only time it should be false is when the premise is true and the conclusion is false. And that happens when Q is false and P is true. So I see another logical equivalence in this table. I see that the implication that we started with is logically equivalent to the contrapositive. So we learned here that P implies Q is logically equivalent to not Q implies not P. And we learned that Q implies P, the converse, is logically equivalent to not P implies not Q, the inverse. These are our relationships. So let's take an example here. Let's take the statement P is, it's raining, and Q is, it's wet outside. And let's practice putting these together as implications, converse, inverse, and contrapositive. So my implication, P implies Q, says, if it's raining, then it's wet outside. And let's look at the converse. The converse is Q implies P. If it's wet outside, then it's raining. And just based on our intuition about how these statements should work, we can see that these are different statements, right? If it's raining, then it's wet outside makes sense to me. Like it'd be hard to imagine a situation where it's raining and it's not wet outside. But I could think of lots of scenarios where it's wet outside, but it wasn't raining. Like maybe I hosed down my lawn, or maybe there was some kind of crazy party where, I don't know, whatever happened and now it's all wet outside. So we've got some intuition that we can rely on here that works out in our favor. The converse and the original implication are not the same thing. If we look at the inverse, we've got not P implies not Q. And this says, if it's not raining, then it's not wet outside. And this statement is logically equivalent to the previous statement, the converse. If it's wet outside, then it's raining. If it's not raining, then it's not wet outside. And finally, we've got the contrapositive. That's not Q implies not P, which would read if it's, oops, let me fix this. If it's not raining, or sorry, if it's not wet outside, then it's not raining. And that is logically equivalent to our original implication. And in fact, if you were to ask me like, hey, is it raining outside? I'd probably say, well, it's not wet outside, so it must not be raining, right? If it's not wet outside, then it's not raining. And hey, it's not wet outside. So this is, the contrapositive is another formulation of our original statement. And we're going to take advantage of that in proofwriting because sometimes it's easier to work with the contrapositive of a statement than the original implication. And that way we can, I don't know, sort of get some advantage from using a different logical form to prove what we want to prove. All right, we're down to our last connective, which is the biconditional. It's this if and only if statement. So P if and only if Q. Sometimes when I'm writing this, I will abbreviate if and only if as if with two F's, one for the first if and one for the second. And you'll see that happen a lot in mathematics. This is another way to say this is P is necessary and sufficient for Q. And if you remember how we use necessary and sufficient for implications, P is sufficient for Q means if P then Q, so that's the if part. And P is necessary for Q is the only if part, or the then. So this is really saying P then Q and also P if Q. All right, so let's work out the truth table for this implication. And when I say work it out, what I really mean is define it. So this is going to be true twice and false twice. So I have true, true, false, false, and then I've got true, false for Q. P if and only if Q is going to have the same truth values as the statement P implies Q and Q implies P. So I'll let this be an exercise for you to do to check this. But we find that those truth values come out to be true, false, false, true, which makes sense, right? An implication is true if both parts are true or both parts are false. So P implies Q or Q implies P. Both of those are going to be true when the truth values of P and Q are both true. It's going to be true when both of them are false. And it's false when the premise is true and the conclusion is false. And since Q is both a premise and a conclusion here, like if Q is false and P is true, that means that P implies Q is true. And if Q is true and P is false, that means that Q implies P is false. So that's the way that we define the biconditional, the if and only if. So that is the definition of our truth table. And it comes from thinking of this as a double implication. It's the implication P implies Q and the implication Q implies P. Most mathematical definitions, even though they're written as if statements, they're understood to be if and only if statements when we use them. So they're used as if and only if statements. And we can read them that way. They're not technically written that way because, you know, we're actually defining something. So, you know, it's hard to say like, a matrix is symmetric if and only if it equals its transpose, because we didn't know what symmetric meant until we defined it. But when we're using it, we're saying these are really the same condition. So we could think of it that way. A matrix is symmetric if and only if it equals its transpose. So the way that we use them is we use them to say these are equivalent things. All right, the final things I want to talk about in this video are the ideas of tautology and contradiction. Tautology is a statement that's always true. And a contradiction is a statement that's always false. And let me give you some examples of these. So if we take P or not P, and we think about its truth values, well, we've only got two truth values for P, right? We've got true and false. And the disjunction is true when one of the component parts is true. So when P is true, it's true. When P is false, not P is true. So the statement P or not P is a tautology. It's always true, no matter what statement P we start with, right? Hamilton College is in Clinton, New York, or Hamilton College is not in Clinton, New York. Like, well, yep, that's true, but it didn't tell us a whole lot. Contradiction is similar. Let's take, as an example, P and not P. For an and statement to be true, for the conjunction to be true, we need both of the component statements to be true. Well, when P is true, not P is false, which makes the conjunction false. And when P is false, that makes the conjunction false. So we've got a contradiction. It's like saying Hamilton College is in Clinton, New York, and Hamilton College is not in Clinton, New York. Like, well, you can't have it both ways, buddy. Either it is or it isn't. And so that's an example of a contradiction. And I believe that is all that I wanted to say on the subject of implication, biconditionals, and tautologies and contradiction. I'm going to have to think through a little bit about what I said right here, because I think I may have gotten it backwards. But the gist of that is the necessary and sufficient is taking care of the if and the only if. I think I may have gotten them backwards. Right? P only if Q is saying Q implies P, and P if Q. No, P, okay, anyway, I'm gonna stop talking and I'm gonna write exactly what I mean for you and put it in the comments. So the gist is you get both of the directions that you need here. So sorry for messing this up, not just once, but possibly twice. All right, next topic we're gonna talk about are these wacky things called quantifiers, and that'll be in the next video.